original telegraph system was based on ancient signaling systems utilized by many civilizations throughout history, all of which allowed one person to communicate with another person across large, sometimes even quite vast, distances. In some cases, this meant using drums or horns or other audible mechanisms. Other times, it meant flags of various colors and shapes to signal a general, for instance, that reinforcements are needed at a particular location on a battlefield, or for a ship to notify another ship that they wish to parley, to have a friendly discussion rather than fighting each other. At times, these mechanisms would extend into human-driven networks, with one flag bearer signaling another flag bearer, who would raise their own flag after seeing the first flag to signal yet another flag bearer further along the path, and on and on and on, a string of dozens of people passing a message from one location to the next, perhaps many miles or tens of miles away, utilizing a chain of flags to pass that message onward down the line. This mechanism was improved upon by the aforementioned telegraph system, which formalized the often flag or horn or other simple message transmitting system into a network of towers that could transmit textual information from tower to tower across vast distances, using a simplified alphabet, communicated using a custom semaphore system, which was something like the flags used by ships and on the battlefield, but made more complex so that adjustable arms atop a tower could be used to send a sequence of information to a neighboring tower, both utilizing telescopes to see each other, and that information could then be relatively quickly sent from tower to tower to tower, connecting remote portions of an empire to more central portions, faster than a human on a horse could travel. Another variation on this theme used what's called a shutter telegraph system, which used light and a covering over that light either from the sky or some other light source, to transmit information using a common code, with some number of flashes followed by some number of non-flashes, representing different concepts or letters. Electrical telegraphs eventually replaced semaphore and light-based telegraph systems, even the quite extensive and heavily invested in ones built by Napoleon around his empire when he was in charge, and spending heavily on such organizational rulership-enabling technologies. And these systems accomplished very similar ends using somewhat different means. Instead of using flags or pulses of light to communicate meaning across distances, they used pulses of electric current across wires. There were two main early models of the electric telegraph. One that used electromagnetism to cause a needle on the receiving end of the message to point at words or letters on a board, sort of like a Ouija board, but instead of supposed ghosts controlling what's being pointed at, you had electricity coming across a wire, showing you on your board what the person in that far-off neighboring telegraph station wanted to say to you. The second, and the one that eventually became dominant because it was cheaper to train operators than to build the more expensive and complex infrastructure required for that needle method, was called the pulse system, though it eventually became known as the Morse system because of the language of pulses a man named Samuel Morse developed in 1838, which allowed operators in one station to tap a little device, which looked something like a record player needle, to create pulses along an electric cable. Those pulses would be transmitted across that cable, creating little blips, little clicks on the other end, and those clicks could then be translated by the operator of that station, the meaning written out using letters on a regular piece of paper, before either being delivered to someone nearby as a letter or a verbal message, or being passed on, re-encoded into pulses, and sent to the next telegraph station. The world of telegraphy was iterated and upgraded over the subsequent years, and a variety of user interfaces were invented with the intention of making the relatively steep learning curve obsolete, so that people could more quickly learn to use these communication devices without having to learn Morse code, before then becoming super speedy at both translating it by ear and retranslating ordinary language into this electric pulse transmission code. Teletype machines of various shapes and sizes were developed, some of which looked something like small pianos, which allowed those who played them to type out messages on a sequence of white and black keys, and in some cases using chords of letters to create more complex meaning, which would then be translated into pulses and sent along electric telegraph lines, passed from node to node on this network, and eventually printed out as raw language at a telegraph office using what were called teleprinters. Other devices evolved from the shape and logic of the typewriter, and it was this style that eventually became the most popular, leading to the eventual evolution of the word processor and the early computer terminal, both of which forked off from this electric communication mechanism, which allowed a relative amateur to sit down at an electric telegraph terminal, type out some kind of message, and then have that message automatically, or relatively automatically, encoded into pulses of information, that information wrapped up into packets, containing what became known as bits of data, some of which stood for letters or punctuation, and some of which served as what you might call infrastructural formatting information. Data about how the message should be converted, who it was for, whether it was private or even confidential, and whether it should be translated by the office receiving it or passed right on to the next office. These data packets also contained information that designated where a message began and where it ended, which again made the training of telegraph operators a whole lot simpler and less prone to error, as before this organizational mechanism was baked into the process, each and every operator had what amounted to an accent or a unique handwriting structure in the way that they spoke and interpreted on this network, which worked quite well, all things considered, but the broader the network and the more variation that existed between the expertise of the users, the more of an issue these sorts of variations became, including when it came to relatively simple things like knowing where one message ended and another began. Jumping forward in time a few decades, as computers became more common in the 1970s, and as organizations and academic institutions began to link their on-site computers with each other, using phone networks primarily, to allow these machines to communicate back and forth across short or vast distances, using pulses on those lines, the same issue arose of how best to encode meaning in a way that would be relatively simple to pack that information up on one side and have it easily unpacked and understood on the other. A paper was published by the Institute of Electrical and Electronics Engineers in mid-1974 entitled A Protocol for Packet Network Intercommunications, which outlined a protocol, a set of rules and standards, an operating guide, for internetworking these machines, allowing them to share information and resources between network nodes, between computers that were on this network connected in this, at the time, somewhat informal way. What was called a Transmission Control Program, or TCP, was developed, which was something like a more complex telegraph system that would take raw language, chunk it up into appropriately sized and laid out packets of pulse data, and then send that data between nodes, unbundling it on the other end and retranslating it back into comprehensible language, or quite often in this case, comprehensible computer code, which the computer on the other end could then do with what it liked. This TCP system was eventually expanded into the Internet Protocol Suite, often called TCP/IP, the IP standing for Internet Protocol, which sliced up this broad-based set of rules and routines into 4 sets of the same, each focused on a different aspect of internetwork-related things, including communications within a single network, communications between networks, host-to-host communications, and process-to-process communications. That last one focusing on the exchange of data between applications on these machines. Like those electric teletype machines and teleprinters, this cluster of protocols combined bits of information into packets. In most cases, packets that contained so-called octets, or 8 bits of information. A bit in the world of computers generally representing a 1 or a 0, and those 1s and 0s being combinable into different meanings, based on different libraries or languages that you might choose to use. In some cases, for use in the world of Internet Protocol addresses, for instance, you can combine those bits, those 1s and 0s, into a series of 3 numbers, ranging from 0 to 255 for each packet of 8 bits. The current dominant model of designating what address a particular computer or other device has on the larger internet, the broad swath of networks all connected to each other in various ways, is through the use of what's called IPv4, which is the 4th version of the Internet Protocol address system, which utilizes 4 sets of octets, those clusters of 8 bits, each representing numbers from 0 to 255, and those numbers separated from each other by dots or periods or full stops, whatever you want to call them. So if you're connected to the internet right now, your device, each of your devices, has an IP address, and chances are, right now, leading into the early days of 2020 at least, that address will be a sequence of 4 numbers, divided by dots, each number ranging from 0 to 255, because that's the amount of numerical information that can be sent using 4 packets, each containing 8 bits of data. Sent across the wires and wavelengths that allow us to communicate with each other using these devices, most of which have agreed to talk to each other using this set, the IPv4 set of formalized rules and regulations. What I'd like to talk about today is what happens when we run out of these types of addresses, and what it looks like when we try to implement new communication structures when one rapidly aging way of doing things has become the very well entrenched default. You're listening to Let's Know Things. I'm Colin Wright. If you are finding any value in this show, consider helping to support it by becoming a patron at patreon.com/letsknowthings. Contributing any amount of money each month via Patreon will provide you access to a call-to-action free show. This is a call to action that you're listening to right now, by the way. You'll get a stream that has episodes that do not have these little segments with me asking you to help support the show, and you'll also gain access to an additional episode of the show each month. Folks who contribute monetarily in this way are the reason that I'm able to commit the time that I do to this project each week, and thus I am thrilled to be able to offer that additional episode of the show and other little bonuses here and there as well. A huge thanks to everybody who's helping to sustain this show, either monetarily or by sharing it with their friends, leaving reviews, other non-monetary methods of support of that kind. That means a great deal. Thank you very much. I appreciate you. All right, let's get back to the show. The Internet Corporation for Assigned Names and Numbers, or Icann, is a nonprofit based in Los Angeles that does a variety of Internet-related things, but primarily, and arguably most importantly, focuses on managing the implementation behind and infrastructure underpinning the numerical and namespaces that serve as unique addresses on the Internet. Now, what that means in practice is that the domain names many of us use on a daily basis, the .coms and .co.uk's and .orgs and .nets that allow us to quickly navigate to websites of various kinds built by people around the world, those are managed by Icann. It also means that the IPv4 addresses I mentioned in the intro, the series of 4 numbers separated by dots, those numbers ranging from 0 to 255, those are also managed by Icann. And important to understand here is that those numbers, those IPv4 addresses, those can allow you to navigate the web, just like typing in a word-based address. If you type in 8.8.8.8 or 8.8.4.4, you can visit Google, while 1.1.1.1 is managed by Cloudflare. Most IP addresses are not public-facing, in the sense that you can type them in and see something on the web, because the device at that address is not set up to accept visitors, or you must use some other non-web infrastructure to access the file systems on that device, while other devices have outward-facing infrastructure that displays as a website, or some other kind of interface that allows you to access what is contained on that device using that address. It was recognized fairly early on, though, that remembering strings of numbers makes a sort of sense for contacting a friend on the phone, but it makes a little less sense if you're trying to build something more akin to a street address system. Thus, the domain name system was established to allow people to purchase more memorable addresses, those .coms and .orgs and such, which they can hook up to their web pages, which already have IP addresses at which they can be found, those strings of numbers, so people can visit those pages without having to memorize seemingly random strings of numbers, something that computers are pretty good at, but most humans far less so. So Icann manages these addresses, these means of connecting devices across networks around the world. And while it began its life as a U.S. government sub-entity, part of the United States Department of Commerce, in October of 2016, the organization and its functions formally transitioned from United States stewardship to that of a global stakeholder community, meaning, basically, that the US would no longer regulate and support the organization all by itself, and the organization would instead be private, separate from any single government's mandate, operating more globally, despite its physical location in California. And that, I think, sets the stage nicely for the first of two articles I'd like to address today. The first piece comes from Ars Technica, and it's entitled, "Despite Clear Warnings, Europe is Out of IP Addresses Again." In late November of 2019, the Réseau IP Européen Coordination Center, the European, West Asian, and former Soviet Union Regional Internet Registry, which is located in Amsterdam and which has a branch office in Dubai, announced that it had run out of IPv4 addresses. In practice, for most people, this will mean very little. When you log on to the internet at home, for instance, you gain temporary use of an IP address owned by your internet provider, and thus, most users will be able to continue using these temp IP designations, whether they're at home, the office, a coffee shop. Those addresses are already in the hands of these internet-providing entities, and are shuffled around every time someone new logs in, and have been since they were introduced. The issue here arises, instead, for certain types of businesses, in particular, businesses that wish to claim their own IP addresses for their own internal or external, the loaning out to other users, use cases. There is currently a waiting list for such companies, and if you put your name on that list, you'll basically have to sit and pray to the internet gods that some other company dies, or likewise gives up the IP addresses that they hold, so that those addresses will be shuffled and will go back into the deck, go back onto the market, much like a telephone number. This isn't something all companies need to worry about, but it's particularly alarming for anyone operating within the internet services or cloud computing space, as they won't be able to snatch up any new IP addresses to use, and thus, in some cases, won't even be able to enter the market, which consequently means less competition when it comes to internet service providers, but also all sorts of other tech companies, any that in some way rely upon this fairly fundamental piece of online infrastructure to exist, or to compete on equal terms with existing companies that provide the same or similar products and services. Now, this was not an out-of-nowhere surprise for this particular market. It's happened before, as the RIPECC was receiving its final batch of IP addresses from Icann. They warned their constituents that this was impending in an attempt to get the main players on board with necessary upgrades, but it didn't work as well as planned. Some ISPs, among other companies, updated their networks and agreements to work with incoming, newer standards, but most did not, and are only now beginning to adjust to this new reality, in the cases where they're not dragging their heels intentionally, at least. The upgrade in question is what's called IPv6. Because of the nature of IPv4, the quantity of possible number combinations that can be made using that many digits in that setup of 4 sets of 3 numbers from 0 to 255, there are a maximum of about 4.2 billion total addresses possible. And we've been long approaching that cap due to the immense increase in IP address use around the world. These addresses being used for everything from laptops and smartphones to security cameras and smart toasters. Anything that connects to the internet needs one of these addresses. And the number of things in our environment that connect to the internet has been ballooning of late, hence the increased rate of use. The IPv6 standard, in contrast to the 4.2 billion possible IPv4 addresses, allows for the deployment of 340 undecillion individual addresses, and an undecillion is a 1 followed by 36 zeros. It's a very, very big number. This is possible because the IPv6 contains 8 groups of 4 numbers, each separated by semicolons, and those digits are hexadecimal digits rather than purely numerical, meaning they can be either numbers or letters, which basically means there are more possible characters and more total slots for those characters to occupy. So the total number of possible arrangements using this upgraded format adds up to 340 undecillion possible addresses, which seems pretty great, right? I imagine it will be at least a few years before we use those up, hopefully, maybe a decade or more. So it makes sense that we'd want to shift over to that standard sooner rather than later, to jump ship on this outdated IP model that we're currently using. And this is true to a point, but it leaves out a few issues that are apparently fairly important to those entities that make up the backbone of the internet, the ones that exist between most of us and regulatory entities like Icann. First among those issues, and probably the easiest to explain, is that there are embedded interests in place that benefit from keeping new competition from emerging, and thus from upgrading too quickly. If there are few, or in some regions no new IP addresses available, that means you don't have young, upstart companies moving in on your turf, challenging your dominance, forcing you to compete, to lower your prices, to offer better services, and so on. It's arguably in the financial interest of these existing larger companies, then, to take it slow in adopting this new standard, because if they don't implement it or do it in a very sluggish way, they get to enjoy their existing competitive landscape for a little bit longer before new barbarians arrive at the gate. Second, though, and moderately more complex, are the issues that exist between network providers, more specifically, with contracts between these networks which are called peering agreements. Some of these contracts are essentially just handshake-grade agreements, and some are highly legalized and multi-signature binding. But whatever the level of casualness or formality, the purpose of a peering agreement is to allow traffic to move from one portion of the internet to another. If you imagine the whole of the internet as a giant web, connecting all the devices connected to the internet to each other, some of those portions of web, nodes that exist within a particular city or region, for instance, exist on a network powered by a particular company, an internet service provider. So maybe Time Warner, or Comcast, or Virgin, or T-Mobile, or AT&T, the company that you pay to allow you to get access to the internet, that's who I'm talking about here. Peering agreements between these providers say, in essence, that we will be sending data from our part of the web to your part of the web, the part of the web run by other companies of this kind, pretty constantly. And the same is true in reverse. They will be sending data to our part of the web from their part of the web. And that means it makes little sense to keep super harsh tabulation of who owes whom how much, because it'll likely be fairly equally balanced. A whole lot of data going from one part to the other, and vice versa, so we'll just call it even to keep things simple. In some situations, though, more specifics are required, and the back and forth flow must be tracked in great detail, with these peering agreements designating prices, how payments will be made, and other things of that nature. And these more formal contracts mostly exist between the world's biggest internet service providers, and it's a fairly small portion of the overall web that uses them. The most recent reliable data I could find said 0.5% of all of this type of agreement as of 2011 fall into this more formal category. The only other time these formal contracts are used is when there's a massive imbalance between providers, to the point where one side is abusing the relationship with the other, leaning more heavily on them than they are being leaned on in return. And as a result, some kind of disparity bridging payments are probably in order. With the dawn of IPv6 and the relatively slow uptick in use of this new standard, some small internet service providers have been making moves to upgrade their systems as completely and quickly as possible. And this is causing commotion for the usual reasons, big players not wanting these smaller players to step in with what they hope will be a near future advantage, maybe allowing them to bulk up and steal market share and become a bigger player, but also for peering agreement related reasons, like the sudden shift in traffic flow and the consequent, hey, we need to rethink this gentleman's agreement we've got going conversations happening between formerly fairly equal peers. This has led to a situation in which IPv6 is somewhat unreliable compared to IPv4 because some networks are refusing to take traffic or are slowing down traffic that utilizes the IPv6 standard. As a sort of retaliation or as a means of preventing these quickly upgrading would-be contenders from claiming too much first-mover market share. In other words, IPv4 internet traffic moves as fast as the local internet allows, while IPv6 internet traffic might be, in some situations, artificially slowed because it isn't necessarily able to take the shortest path from point A to point B across that web of the internet. This is a problem that has little to do with the protocol itself, which would seem, by all indications, to operate in exactly the same way as the previous protocol as far as we users are concerned at least, But there is an issue of economics and an issue of governance in that entities like Icann and the RIPECC have been unable to nudge or incentivize the businesses that they govern to widely adopt this new standard that they've worked so hard to make available, and which has been around in some form, mostly as a draft standard, a standard that was still being worked on for about 2 decades, but which has been an official internet standard, which means it's been fully baked and ready to go since January of 2017. So while there are still technical preparations that are part of the problem here, most of those problems are relatively simple to solve, as tech infrastructure goes at least. Tools have been provided that allow for the temporary conversion of IPv6 and IPv4 traffic back and forth, sort of like an adapter that you might put at the end of a cable to convert it from one type of USB to another. And full-on conversion resources have been made available by these regulatory bodies for years as well. Much of the issue here, then, is less about the technical and more about the economic and political. And unfortunately, we've reached a point where this evolutionary sluggishness is causing secondary consequences to entities that are not themselves, mostly at least, part of why this standard has yet to be adopted whole hog. This issue is likely to continue for years, if not longer, despite the solution, or at least a significant chunk of the solution, already existing in an easily adoptable form. Until then, though, we're likely to see more disruption across internet-reliant and internet-adjacent industries, and new and exciting types of grift, like the recently uncovered sale of tens of thousands of IP4 addresses for personal enrichment by an employee of the African Network Information Center, which is the African and Indian Ocean region manager of these addresses, similar to Icann and the RIPECC. These stolen addresses are estimated to have been worth over $50 million on the open market, and this backdoor sale of what are supposed to be fairly well-regulated assets contributes to spam and phishing issues when such addresses are purchasable on the unregulated black market. The second piece I want to comparably quickly address here, because it's connected in some interesting ways to that first topic, comes from Mashable, and it's entitled Powerful Internet Authority Says It is Powerless to Stop $billion.org Takeover. The Internet Society, sometimes acronymed as ISOC, is a nonprofit based in the US that was founded in 1992 to, in their words, quote, promote the open development, evolution, and use of the Internet for the benefit of all people throughout the world, end quote. Generally viewed as a broadly beneficent entity in the internet world, ISOC, among other things, has helped build community-owned internet networks, helps researchers around the world connect with other researchers and share their work, and helped test IPv6 deployment in mid-2011 to ensure the standard was up to the task of eventually replacing IPv4. ISOC also, back in 2002, bid on and successfully purchased the .org domain registry, meaning they bought the right to sell .org web addresses from Icann and set up a separate nonprofit called the Public Interest Registry to manage it beginning in 2003. This nonprofit, like its parent nonprofit, also enjoyed quite a bit of goodwill as a result of their actions, helping developing markets to get online, doing a great deal of free work to protect people using the internet, and coming up with upgrades to various protocols and systems that keep the net operating relatively smoothly. It came as a bit of a shock, then, to a lot of people in the internet-focused tech world when it was announced that the Internet Society would be selling the Public Interest Registry, the nonprofit that they set up to manage and sell these .org domains, to a private investment firm called Ethos Capital. This, to many people, meant that not only would .org domains suddenly be open to the same price gouging and manipulation as many other top-level domain names, leaving a lot of nonprofits in particular beholden to the whims of this investment company that would henceforth be setting the price on their web addresses. It also meant that the Internet Society, long seen as a truly wonderful force in the online world, had kind of slapped these other nonprofits across the face in doing so. To make a quick buck, they'd sold what's become seen as a foundational structure of the web-based world, or so it seemed at least. Since the announcement of this sale, petitions have been signed, thousands of letters have been sent, organizations as diverse as the Electronic Frontier Foundation, the Internet Archive, the Wikimedia Foundation, and the Girl Scouts of America, among many others, have spoken out about their opposition to this sale, which they believe could lead to vastly increased prices, Whatever this buyer thinks they can get away with, really, alongside censorship and/or arbitrary decisions to shut down websites that don't agree with their business model or ideology. A member of the board of the Internet Society named Richard Barnes wrote a blog post in response to these concerns and criticisms, saying that he understood their worries, but also that this sale, first, probably wouldn't lead to those outcomes, as the buyer said they would limit price increases to 10% a year, max, and they would seek certification as a B corporation, which would allow them to pursue goals other than purely financial ones. But also that the sale would allow the Internet Society itself, that organization that sold the registry, to do so much more than it was already doing, and to be liberated from just one trickle-based income stream, the .org registry. So after the sale, they could invest in other assets which would make them more resilient and more able to do the good work that everyone knows them for. We'll have to wait and see how this component of the online real estate shortage plays out. There's word as of the day I'm recording this that Icann is now taking another look at this potential sale, and though it's generally thought that they can't really do anything about it, they do not have the power to stop it, they could potentially slow it down substantially, even to the point where the buyer loses interest. But it's a fair bet that however this particular instance shakes out, this and other instances of bureaucracy and business determining in many ways the shape the fundaments of the online world take will further amplify the differences between portions of the growing splinternet, the forking of the internet into different shards, distinguished by governments and by dominant business models, by approaches to things like tracking and data and privacy, and various economic realities, while also potentially setting the stage for completely new offshoot technologies. After all, technical debt and fractured infrastructure and different views of how things should evolve often serve as the catalyst and impetus behind investing in new, sometimes parallel, sometimes entirely novel systems that help achieve the same outcomes, but which then eventually show themselves to be useful for entirely different purposes as well. Just as the internet evolved from earlier technologies like the telegraph, there's a chance that what's happening now with our current iteration of these interconnected communication systems could nudge some small portion of current internet users toward building and fleshing out some next step innovation. It could also be that the next step is that splinternet, and what we'll see instead of an internet competitor is a far more complex and diverse and less homogenized web of interconnected devices and people using those devices, managed and maintained by entities with a wide variety of ideologies, powers, intentions, and visions of the future. If you're enjoying Let's Know Things, consider becoming a patron at patreon.com/letsknowthings. Monetary contributions of this kind, of any size, any amount, each month, are what allow me to commit the time that I do to this project each week. It's what has allowed me to slowly but surely increase the amount of time that I commit to it, and it's what allows me to produce extra episodes each month for folks who are contributing at any level. If you're enjoying what you hear, do please consider popping on over to patreon.com/letsknowthings and becoming a patron. A huge thanks to everybody who's already contributing in some way, shape, or form, either financially or non-financially, by sharing the show with a friend, sharing it on your social network of choice, and or leaving a quick review wherever you get your podcasts. I had no idea what to expect when I started this podcast, but it's your enthusiasm and support that has encouraged me to double down and commit to it the way that I have, and it's the reason that I continue to enjoy producing this show the way that I do each week. Thank you very much for your support and enthusiasm. The book that I'd like to recommend today is called The Influential Mind: What the Brain Reveals About Our Power to Change Others by Tali Sharot. This book is dense with research, some of which was conducted by the author herself and her team, and some of which is just research that has been conducted elsewhere in the sociological and psychological sphere. All of the research presented, though, is couched in well-written explanations of what it means or what it might mean, how it interacts with other types of research that's been conducted, and explanations of what we might take away from this research, what it might mean about our ability to influence others and our ability to be influenced in return, and how concepts like influence interact and clash with what we know about the brain and biology and how these things all fit together. Now, if any of that sounds interesting to you, consider picking up a copy of The Influential Mind by Tali Sherritt. You can find out more about me and my work at colin.io. My blog's at exilelifestyle.com, and you can find the show notes for this episode and every episode of the podcast at letsknowthings.com. If you're enjoying this project, you might also enjoy my other projects, Ask Colin and Brain Lenses, which you can find at askcolin.com and brainlenses.com. Feel free to reach out and say howdy on your social network of choice. I'm at Colin is my name on Instagram and Twitter, and I'm just Colin Wright on Facebook. Thank you so very much for listening. I'm Colin Wright, and I'll talk to you again next week.